Hello guys, today I will be explaining my project Network Traffic Congestion Prediction. This is an end-to-end ML project that focuses on a pipeline which will generate data, feature engineer the data, pre-process, and then train the data, and then we'll have some evaluation, and then as well we'll create an inference end using Flask, a simple inference end to access our model. So without further ado, let's get started. Let's activate the environment. Let's open our VS Code. So this is the project directory, as you can see. So first, let's get through our EDA notebook that I've performed. I did this using Google Colab. So we'll understand our code from here, and then we'll understand what the other files and project directories are. So we've used modular coding everywhere. Um, like to ingest data, feature modeling models, and for login also we've added also visualization. So this is the end-to-end ML project. Now let's get into the project and you'll understand what I mean when this is a modular. So network traffic congestion prediction. The first thing what we'll do is we'll import our necessary libraries that are required for any data science or machine learning projects, pandas, numpy, sklearn. We take some train splits. We are using random search forest for this model for this project. So we've been importing everything, and then we'll even save the project using pickle. So we have other basic libraries, matplot, seaborn for visualization, and yeah. So what we did here is we created our own data instead of looking for in the internet. So I've used a simple Python code using numpys and pandas to generate some random data and realistic data. So I've added some functions like called traffic pattern to generate the data in a more realistic way. So during peak hours it will generate higher values, and in the off peak hours it will generate less values. So we are generating packet size, bytes and source IP, destination IP, protocols, and the congestion, which is the target table for our project. So we generated the data set, let's say 1,000 rows we've generated here, like we've mentioned n samples 1,000. You can make it 5,000, 10,000, anything you like. And then we've saved it into a CSV file. Once that CSV file is saved, we will load the CSV file, and then we will do some exploratory data analysis, obviously. So we checked the first 5 columns of the data using df.head info to know what's in the data, and also to see the data types and all. And then the basic mathematical functions like maximum value, standard deviation, 75 percentile, everything. Also the shape of the data. So once that is done, we've checked the class imbalance. So we, as I said, we generated some target variable was congestion, 0 for congested, 1 for not congested. Yeah. So two classes are there. We see the class is not that imbalanced. One is around like 450, I guess. One is around 510, 480, 510 something. So then we've also created a time series analysis chart using this timestamp column we have generated, and using the bytes and. So we are seeing like the traffic volume for each day, and also 24-hour rolling average time through this yellow marker. Then we've also seen protocol distribution. We've used three protocols: HTTP, UDP, TCP. So you can see it's not that imbalanced also. So our data generation has been uh, fair enough. It's good enough to continue our project. So yeah, again, congestion over time is also being generated. So once that is done, we'll be engineering our feature engineering, because pre-processing we've generated data. There's nothing much to pre-process there. So we directly went to feature engineering. So what we are doing is the IP addresses we are converted into integers. So we converted all the IP addresses values into a integer so that our model, it will be easier for our model to train in numerical values. So we've derived new features also: packet size, mean, bytes, send, sum, also packet rate also. And then we've also extracted the time from the timestamp, like day of the week, is it a weekend, or which day is it. And also we generated earlier, hour and day also from the timestamp, as you can see in time series traffic over volume. So we've generated df.hour, df.day also to understand more about the data. So once we have done that, we're dropping the original. Yeah, so we've also done one encoding using get dummies. So there was this column protocol which had three values: TCP, HTTP, and UDP. So we've done one hot encoding for them. So we passed a numerical representation for those categorical values. So then we dropped all the original columns, like source IP, which we converted into numerical. So drop that, drop the day, because it was causing some issues using date time issues. It was not getting converted, so we needed numerical only. So decided to drop the day one. So once that is done, we've scaled our feature numerical features using standard scaler. This is done so that it's easier to train our model. So large values won't like affect our models. It gets scaled down to normal values, normalized value. So once that is done, we're training our model. So we have dropped the congestion table, and it's the target table. So we've declared our target table here. So we've split the data, train and test split. So training is 80%, test is for 20%. And then whatever data we are using for training, we've saved it into a pickle file for later when we are using it in inference side. So then we have time series cross validation also here. So since this is the time series data, we cannot afford to lose values here. So we're using time series cross validations to get each and every data. After that, we've determined some parameters like n estimators, max depth, minimum sample split, minimum sample leaves for random tree forest. So this is basically like a hyperparameter tuning. And after that, we've used grid search to check for the best model according to the F1 score, the best combination, which combination is the best for this model. So once that is done, we've tested the model for its evaluation. So we've got the accuracy of 0.92, which is not bad. It's a pretty good score for this. But obviously, we're using synthetic data, so we can't really rely on this. That's a dummy project. So yeah, so we've got an accuracies of 92. So I did this hyperparameter tuning because when I just used the random forest, I got an accuracy of around 0.62, which I was not happy with. So I decided to just take a tweak in the model a little bit. So yeah, we've got a good score here. Once that is done, we plotted the confusion metric graph also to check, like, yeah, how many predicted labels were actually true and how many predicted labels were actually false. So yeah, you can just go through them. I will printed out additional metrics also. Precision we already saw. We saw for recall, area under the curve also. So once that was done, we checked which features had the most importance in the models. So we got to know that timestamp per seconds was the highest important feature or column in our dataset, and the rest are as follow. So this is also useful when you are, once you want to retrain your model again, and then you get more insights on which features are much better for your purpose. Once that is done, we've saved the model again. We've saved the both congestion model where the actual random forest model is there, and the scalar pickle file, which is scaling the data, which has the scaled data. And additionally, before I told you, we saved the dataset also x dot file pickle file. So once that was done, we created a small prediction inference function to check our model is returning good value or not. So we have the user input in, and then it goes to it fetches the model, it inputs the values in the model, and we get the predicted output. So I've used this input data here. So we got our prediction for one input data was 1 and for the other was 0. So we can see our model is working. Now I will go through you the I will run the code for you. This was the model EDA notebook. So now we'll look at the ML end-to-end project part. So what we have done first here is we've declared a config file. Over here we are predefining the values that will be used throughout the project, like the model trainer. We've like already model parameters we've already saved here, the details for model, also the numerical features we've already saved here, the paths where everything will get saved, even the login info where it will be saved, like every value that can later be used in the code. So you will see ahead what where it's been used. I'll go through them. So we'll have a folder called data for traffic data. We'll have a folder for logs. We'll have a folder for models. We'll have a folder for models. Yeah, sorry for the uh, machine delay. So we have this scripts file. With this run pipeline will actually run everything. Yeah, models was here where all the models will get saved. So under the SRC we have the various modularized code. So you can see data, we're generating the data here. We have features, we are doing some feature engineering here. We have the models, which is predicting and training the model. We have the utils file where the logger is defined, and we have a visualization file that will visualize. And then we have the Flask part here. I will go through them ahead. And then we have some folder to save all our visualizations here. Visualization. So what I will do is I will delete this file right now from here, just so that you can see it's getting generated. I'll delete the logs file from here. I'll delete these models as well, and then no, notebook I will not delete. Scripts, no need to delete this. I'll show you in a while. SRC, there's data, generate data, everything's here, nothing much to delete here. And then we have the visualization where the visualization will be created, and then we'll delete them as well. Okay, okay, so let's go through the code. We have the SRC folder where there is another subfolder called data, and there is generate data.py. So as we saw earlier that we had created our own data, so we have the same function here written in a better way. For the same logic is implied here, almost everything is same here, and then we can run this code to see if our data is generated. So this is the same code modularized and breakdown here. Now we'll go through the feature folder where there is feature engineering code. Now this is again the same code which we used earlier, which I showed you earlier for feature engineering. So I've just added some function. I've just turned it into functions to take inputs. So here are like the same parts here. We're converting the IP addresses into integers. We're calculating the packet rates. We're timestamps. We're one hot encoding the categorical features. We're dropping the unnecessary columns. Everything same like before. We've also scaled the data over here only in the feature engineering itself. Uh, Now we will go to the models part where this is the train model. So here we are training our model again. The same things we declared earlier, it's the same code here. So now what I was talking about, the YML file, you can see. So yeah, you can see I've used the config file, the YML file like this. So you can see model path. At first, I've imported the config file over here. Config path equals to config.config.yml. So I've imported this path over here. So we've opened the config YML file, and then we see the model path. I've declared it like config.paths model path. So if you just look at here, config.paths model path, and it shows model congestion model.pkl. So this was the folder over here where everything gets saved. We just deleted the models earlier. So you can see this is how we are using the YML file. Now going ahead, we had the predict.py. This is for the same function we used like to predict our condition in the last. It's the same function over here. We've created a function to test the predicted input. Once this is successful, we know we can move ahead with Flask. So I've broken down all the codes, modularized it, and then now we have in the scripts folder run pipeline.py. So here we are calling all the functions from the broken down parts of the code. So we've called the generate traffic, engineering features, train model, visualization, logger, and everything, and we've declared everything here, and then again using the config file we've like you know uh, pathed the raw data path and other necessary things also. So you can go ahead and run all the codes here individually to see step by step, but I've created this pipeline, so I'll just directly go and run this. mm, oh yeah, so we just go ahead and run this. Okay, sorry. um go ahead and do yeah, we need to declare the scripts, sorry, the scripts and pipeline. No, no, sorry. Need to go script dot. Yeah, so you can see we got the data generated, we have the log file generated, the models are getting generated, and you can see the logs over here. I'll show you ahead. It's been saved in the log file also. It's still training. Once it's finding the best model right now. So you can see new best model found with F1 score 0.4, 0.55, so it's still training. So it looked for the best model using GERD's search CV. Yeah, so everything done, pipeline completed successfully. You can see the logs, you can see the precision 0.6 and everything. Yeah, so I think something went wrong somewhere. We'll go ahead and see all the files have been created. You'll see the logs. The logs are here. Started traffic analyze, generated new traffic. You can see everything, all the functions executed, the data got generated here, the models are here. Yeah, the visualizations are here. You can see everything's perfect. It ran perfectly. So let me just go ahead and um, now show you the Flask part. So the Flask part is over here. You go over here to templates. You'll have two files, index HTML and predict HTML. These are just basic Flask structure I've created. And then you have a static file styles.css where all the styling is done. And then the main part app.py. So this is app.py. You just go ahead and run this file over here. Then when you open your terminal, see this is opened. You do predict congestion. Now you can keep your packet size to 100 bytes and let's say 9000. Source IP 192. Okay, add 1 0. Destination IP 10 point. Yeah, we can just do this 20 TCP. Now let's go ahead with UDP timestamp. Let's skip hour. skip 4. Yeah, 4. So predict. You can see congestion status was normal. And go ahead again, try 3000, 6000, source IP 192, 0, destination IP 10.0, 0, TCP. Yeah, let's go with TCP this time. Then 1700 hour 27. See, yeah, this is also congested. So yes, you can see the project is working perfectly. Thank you for taking your time and going through my project. This is end-to-end ML project. We've successfully implemented it, and then we can use this to predict the network congestion. So for further enhancement, we can use this same prediction to allocate bandwidth to the less allocate more bandwidth to the more congested area and less bandwidth to the less congested area. So this can be used in a ISP company. Thank you for watching.